Hello, everyone. It's a pleasure to be here to share with you about our group projects, optimizing envelopes for enhanced accident prediction models. In nowadays, where traffic safety is a growing concern, the need for advanced data-driven solutions is more pressing than ever. Currently, our ability to predict and manage traffic accidents is hampered by outdated methods, leading to inefficiency and lack of real-time responsiveness. The challenge is not only predicting accident, but also ensuring that these predictions are continually updated and relevant. We have devised a comprehensive solution that combines the principle of envelopes with our goal of enhancing traffic safety. Here's our understanding the landscapes. By adapting envelopes best practices, we are streamlining our machine learning development process, specifically tailored predict traffic accident severity. This ensures our models are scalable, efficient, and reproducible. Utilizing open source tools allowed us to continuously monitor and manage our machine learning models. This is crucial for maintaining high accuracy and reliability in our predictions, which are vital for real-time traffic safety applications. Our approach to retraining model is driven by data insights and drift detection. This is particularly important in the dynamic context of road traffic, where conditions and patterns can change rapidly. So here's our streamlined workflow. First of all, we will store our historical data in Amazon S3, and then we use Kafka to let the data become streaming. And then we use Spark to do the data processing. And then we store the clean data in Hive warehouse. Basically, we will just build two very important models. The first one is predictive model, and the other one is data drift detections.
So let's go through the architecture. We have Amazon S3 for storage of data, as we discussed. Then we have PySpark, Kafka, Spark Streaming, Hive, and then we have the dashboard and model monitoring, which detects if there is drift detected or not, and based on that, we retrain our model or do nothing. Next. So for feature engineering, we have converted data type to better fit the model and apply the pipeline. We have identified and addressed the data quality issues. We have detected and excluded unrealistic outliers in precipitation and distance. For example, 80% of distance data is recorded as zero. We have developed new features like accident duration time to deepen the analysis. We have implemented random forest and identified humidity, pressure, temperature, and wind speed as significant numerical predictors. Analysis revealed a higher incidence of severe accidents near crossings, highlighting the importance for location-based binary features.
Thank you, Amia. Now let's talk about the MLOps pipeline. So MLOps pipeline has basically 4 buckets. Design, where you're gathering the business requirements, you're in the ideation stage, you're trying to figure out different possible solutions, you're whiteboarding and brainstorming, and you're also trying to gather the sufficient data. From there, you go to development, where you're developing your model, you're figuring out which kind of data sources you host your database on. You are developing, training, testing, and validating your let's say a prediction model. And after you build the model, you're looking at deploying the model. It might be on a CI/CD pipeline in Jenkins or GitHub. It can be on AWS, etc. Then you go to the operations phase, where you're doing active system monitoring and tracking the maintenance. Now, the MLOps streamlining the machine learning life cycle. We've used Databricks for ML experiments, where we've leveraged PySpark ML environment. We've done hyperparameter tuning with cross-validation. We've done experimental tracking with MLflow to track the experiments, hyperparameters, metrics, and model comparisons. We've done model comparison visualization using MLflow's comparison charts. And we've done model registration and deployment, where we successfully register the final model MLflow and explore deployment options for real-time predictions. For the proactive data drift detection for model reliability, here we've implemented drift detection with Evidently AI to systematically monitor and detect data drift in incoming data streams. We've done comparative data analysis against a 2-week historical sample. We've automated reporting in MLflow. We've set up an alerting mechanism to notify stakeholders about detective drifts, and we've automated the decision making on model retraining through a deterministic process for based on drift detection outcomes. Now, let's talk about what we did and how we did it better. First, we took crisis management. We enhanced it with real-time predictions on traffic accident severity, and we've optimized the resource allocation response times. But what we did it better, we built an efficient model development where we followed the best MLOps practices to bridge the gap between drift and ground truth to ensure long-term sustainability of prediction accuracy, which thereby saving hours of retraining and recompetition. We've taken model maintenance, we've made it effortless to drift detection mechanism to streamline the model retraining and set up an alerting mechanism. But we've also enhanced risk assessment by simplifying insurance claims through improving risk modeling, and we've strengthened the real-time risk assessment capabilities.
Ryan and I will be giving a code walkthrough for our project. First is the real-time data ingestion part. Our data is in S3, that's in a JSON format. So we read the files in JSON format and write it to Kafka. So here is a sample look of how the Kafka topic looks like. And these are our raw messages. This is the total count and the retention time period. And to read this, we have written a consumer that sits in Databricks. So this is our read stream that reads from Kafka topic and writes to a sink. That's Hive Delta table. So for each batch for each micro batch that we consume, we do inference of each data point in the real time. This is our model inference part. And we made our pipeline robust by creating a merge logic that detects duplicates in real time and upserts the data.
We begin our ML flow by extracting data from a Hive table, incorporating feature engineering such as creating an accident duration time column to capture the total time from the start to the end of an accident. Further, we employ outlier detection to eliminate extreme values. Next, we will construct a machine learning pipeline. In this chunk, we start with string indexer and one-hot encoder to convert categorical data into numerical format. We then use vector assembler to merge specified columns into a single vector column. This is an essential step for machine learning. Following that, we apply a scatter to normalize features. After doing that, the subsequent step involves building a random forest model for predicting accident severity. We further enhance the model by utilizing grid search to fine-tune hyperparameters, resulting in 28 models with different hyperparameters. Later, we save this pipeline for reference and future use in a streaming part demonstration that we will talk about later. To provide a more comprehensive understanding of the model, we even showcase feature importance. And last one, our success metrics includes ROC curve analysis and an AUC score. As you can see from here, our AUC score is 0.77. And this is the ML flowchart demonstration.
Now comes the ML flow part. This is how we use ML flow in our project. Let's say I want to pick the random forest experiment that we have done. As you can see, there are multiple runs that we have done, and each run corresponds to a cross-validation object. So we used MLflow Spark auto-logging feature. So that gives this nested structure. So for each cross-validation, we have multiple runs. And if I want to compare the metrics for each run, I can use a bar chart view. As you can see, multiple runs over here. And if I want to compare the hyperparameters for this, I can use this parallel coordinate plot. I can list my hyperparameters here, and this is my metric. And how do I interpret this plot is, if I drag this, it will give me, for these set of hyperparameters, I can achieve a ROC score of 0.77. Coming to the model registry and deployment part, as you can see, I have deployed a model. In the version 1, I moved my developed model to staging and I realized that I committed a mistake. Hence I reverted this operation. So I corrected the model in version 2 and released it to production by moving it to staging and eventually to production. That's how things work in reality. Next is the drift detection part. We used Evidently package for this. Here are our columns of interest. I created a train and test set from this, and we used Evidently's calculate function to calculate the drift for us, and we saved the report in HTML format. We also have a email alert feature for this mechanism. As you can see, the entire run is logged as a MLflow experiment. This is how the experiment looks like, and these are our files that got logged. This is the email alert that I've got. As you can see, 0 out of 7 features have data drift. If I download the report, this is how it looks like. The underlying mechanism is a case test where the null hypothesis states that the two samples come from the same distribution. This is true in fact for this case, since there is no data drift. To test our drift detection part, I have also created a simulated dataset which contains almost 70% outliers. And in this case, we have observed drift. So we reject the null hypothesis and state that there is a data drift for this incoming dataset. We can automate this entire process. However, it is recommended that until we gain confidence on the model and incoming data, it is better to retrain our models in a manual way.